Within the humanities field, there are a few technological tools used for learning and even fewer that allow people to interact with the environment to create an enhanced learning experience. An experimental protocol was approved by the Ethics Committee and 24 participants were included to divide into two groups. A control group that will experience a simulation of a traditional class and an experimental group, which will try the Neurohumanities Lab experience. The Neurohumanities Lab is a semi-immersive environment considered an innovative project thanks to a combination between real-time biometric data, with diverse models being used including motion and motion detection, voice recognition, artificial intelligence text generators, and vision systems with facial gesture recognition, all being applied to enhance the learning experience within the humanities field. As emotions play a fundamental role in human experience, influencing cognition, perception, and everyday tasks such as learning, communication, and rational decision-making, the proposed solution aims to provide the individual with the experience of making their learning process personalized. Their electroencephalographic and physiological signals data are constantly in a feedback loop that will modify the classroom environment, such as making changes to images, lighting, sound, and more. The fact that everything in the field of humanities is relative and there is never a right or wrong answer, making the teaching and learning process hard to evaluate objectively. Therefore, the Neurohumanities Lab provides a way to quantitatively and qualitatively determine whether a student is learning or not based on their EEG and physiological data. Data acquisition was made with different devices. EEG data was acquired with OpenBCI UltraCortex Cap via Bluetooth connection with a Python script. Empatica E4 wearable device is also connected via Bluetooth and will register electrodermic activity and photoplasmography signal for heart rate calculations. Methods of signal preprocessing were used and applied in MATLAB to clean the data and remove noise sources other than brain activity. Different features from EEG signals were calculated: total power and power spectral density of all frequency bands in all electrodes, and the engagement ratio in the frontal electrodes in windows of 1 second. Machine learning was used to find which calculated features can help differentiate and classify the data between the control group and the experimental group. First, the minimal redundancy and maximum relevance algorithm was applied. The best features identified were different between each scene. However, engagement ratio in frontal electrodes was present in all of the scenes in the first 10 best features. As well, gamma frequency band was the most common band. The accuracy of training and testing of 3 different supervised machine learning models was evaluated. Results showed the decision tree model was the highest accuracy, approximately 90%, starting with 10 features. Engagement was calculated from EEG signal and it revealed that it increased across the scenes in the experimental group except for scene 1, meaning that engagement is a potential feature to classify but also to identify possible learning experiences among the groups. As well, the decrease of gamma band in the frontal regions compared to the resting state of each participant is said to be associated with presence in literature. Other correlated with presence regarding physiological signals is the decrease in heart rate and increase of eta peaks compared to the resting state of participants. These findings were also present in the result from processing of these biosignals and are congruent with the statistical analysis of the presence questionnaire, which showed the category of spatial presence was significant in the ANOVA and p-test analysis. Dipole fitting is a processing method that allows the clustering of EEG signals components and the visualization of set clusters within the brain topography of the data, showing a centroid which is then used to find the coordinates of the activated random areas. Results from this method reveal that in the experimental group areas of sensory information and emotional responses were activated, while in the control group areas of visual processing and language were more present. The areas in the experimental group could propose the possible futures to research on the role of emotion in relation to learning experiences. In conclusion, the Neurohumanities Lab experimental protocol revealed that there is a difference between the learning experience between a traditional learning and technology-enhanced learning. These differences can be identified in physiological signal characteristics, changes such as engagement, decrease of heart rate, and increase of eta peaks. However, there are still ways to make Neurohumanities Lab a better learning experience and use completely immersive virtual reality settings to improve results.